Okay. Hi, everyone. Can we settle down? Okay, so if you remember, we started this semester by talking about how there's this very deep connection between proofs and programs, right? And so today is the... Sorry, can we settle down out there? Okay. So today is the last lecture of this first part of the course, which deals with proofs. Now, before you start celebrating, this doesn't mean we won't do proofs after this. It's just that after this we'll move on to discrete probability. So, you'll still have to prove things, but now we are not focusing on proofs after this lecture very much. Okay, but what I'll do in this lecture is I'll try to make this connection between proofs and programs much more, there's a very, very deep connection which actually resulted in the birth of computers in the first place. And so we'll talk about that connection today. Okay? So where should we start from? So we'll start by talking about self-reproducing machines. Okay? So, you could imagine, well, if you have a factory for building cars, well, you could make it more and more automated so that they're actually robots who are building the cars. And then you could say, well, that's a great accomplishment, but that's unsatisfying in some way, because after all, these robots who are building the cars know more than the cars do. They're sort of a higher order machine that's building a low order machine. Whereas if you think about life, we have self-reproducing machines. Right? So life sort of reproduces itself, and it makes copies of itself. It's, and I suppose at one point in time, the model was, well, you have an animal, and inside of that animal is a tiny animal, and inside of that tiny animal is another tiny animal, and so on, and it sort of goes on. Each generation sort of makes one of these shells disappear, and the thing inside grows. Right? But we know that's not the case. You actually have. You have these self-replicating beings. So could you do that with a machine? Could you ever build a machine which builds something which is as complicated as itself? Okay. Well, I'm sure you know the answer is that you can. In fact, an example of this is a virus. I mean, a computer virus, right? It's a program that reproduces itself. Now, So once you have this sort of an object which can build itself, or it can, another way of thinking about such objects is, can you build an object that can think about itself, that has a description of itself? Okay, but once you create such objects, you also open up a Pandora's box. So, for example, remember we started this whole part of the class by talking about propositions. A proposition is a statement that's either true or false. Right. Now, there's a certain kind of statement that you can come up with which causes a lot of trouble here. So you could come up with a statement which says something like, this statement is false. Okay, so now, is it true or false? There's a problem, right? If it's true, then what it's saying is true, and then it must be a false statement. What about if it's false? If it's false, then what it's saying is false, and so it should be true. Okay? So, so at the heart of it, this kind of statement, when it was first thought of, it came up in various contexts, and it was just seen as some form of a puzzle. It was just one of these mind teasers, or it was something that was thought of as entertaining, but not to be taken too seriously. And then, starting about a century ago, this kind of statement played a very central role in understanding both, the very deep things about proofs as well as about computation. It's what led to the actual invention of computers. Okay, so this kind of statement, this kind of self-referential statement, and the kind of trouble it causes. People started investigating it. They thought it was a tiny little thread that was loose, and so they started pulling on it. And before they knew it, they had pulled apart the entire vest. Right? It just all came apart. And so that's what we'll try to talk about today. Okay. So let's start by talking about how would you actually create a program that prints itself. Okay, so what you want is to design a program P. So you want to design a program. Okay, it's some program, it's some text, and when you run it, okay, so it should output exactly this. It should exactly, it should exactly output whatever the program looks like. Okay, so how would you write such a program? So let me show you how you do this in English. So in English, you could do it like this. You could say, print out 2 copies. Okay, so just first let's try this. So print out the following sentence. Okay, what do you think? Will that do the trick? No, because see that's a problem, because if you follow the instructions on this sentence, all that you will print out is this part. Okay? So how about if you could when you're writing a program, you could just say print it out twice or something, right? So print out the following sentence twice. So what about if we said print out the following sentence twice, and we added twice? Would that be good enough? Well, it's almost good enough except for the quotes, right? So, let's just add in another instruction saying print out the following sentence twice, the second time in quotes. Okay, so we say, print out the following sentence twice, the second time in quotes. Okay, and then of course we modify this twice, the second time, comma, the second time in quotes. Okay, and now we are in business, right? So now this is a sentence that prints itself out. Right? These are instructions which say, which print out exactly the instructions. Okay? But a program is exactly like that, so we should be able to write a program that prints out its own description. Okay, so let's just write it down. So these a program that prints out its own description is usually called a quine. So let's say we have a program quine. Which does this. It takes as input a string, and it outputs string. Okay, that's what this program does. Okay? And now the program that outputs its own description is just quine with right? Okay, so you can sort of write this in, I just chose a particularly sort of nice syntax in which to write it, but you could do this in any programming language of your choice. You could write out a program that prints its own description. Now, okay, is that clear? Yeah.
Why is there only one set of double quotes in the second string?
Oh, yeah, sorry, because I forgot to put in the second one. Okay, so I'm saying, if you write a function quine which does this, right? Then when you call quine on this input, it outputs exactly right? Yeah. Okay, now this might seem like small potatoes, right? It's sort of, it's not that interesting to have a program print its own description. What we want is we want an arbitrary program that knows its own description. Okay? So how do you do that? Well, to do that, you solve the extra credit problem on this homework. Okay, so what does that say? It says, okay, so what it says is, suppose you're given an arbitrary program, P, that takes as input X and Y. Okay, it's an arbitrary program. Okay. Now, what it says is, given such a program, show how to convert it into another program, Q, which on input X does exactly what P would do on input X if Y was a description of Q. Okay? So you could think of Q as a self-aware version of P. Right? So you want to write down a program P of X, which does something, but now, so you write out the program P of X, you add another variable Y, which does nothing. Okay? And now, you go through this construction, and what you get back is a program Q, which does the same thing as P, so it computes P of X. So now it has this, whatever P did, this was an arbitrary program. Q also does that arbitrary thing that P did, except that Q behaves as though it also knows its own description. Okay? Yeah. Okay. Now, as I said, this ability of programs to know their own description, this is both a powerful thing, but it's also a very troubling thing. And the troublesome thing that comes out of it is things, the thing that we saw last time in class, which was the halting problem. The fact that there's no program that can compute the halting problem. Okay? So which can decide whether a program halts on a given input. It's this kind of thing. It's self-reference, which is what what makes it possible to say that programs are just too powerful. You cannot really look at a program and analyze it in full generality. So you cannot, for example, you would like to know, given a program, is it a virus? Right? You see a string that you've got in your mail, and you want to know, is it a virus? Well, you can't. It's uncomputable. Right? You could throw some heuristics at it, and you could try to figure out, is it, do the following simple schemes for writing viruses, are those consistent with the string that I got? Yes, you can do that. You can analyze it to some extent, but there's no completely foolproof way of deciding whether a given program is a virus. Right? You can show that by this kind of argument, right? Okay, so how many of you remember the uncomputability of the halting problem. Deciding that a machine halts on a given input, that there's no program that'll do that. Do you want to see it again from a different viewpoint? Yeah? Okay. Okay, so let's look at it again from this viewpoint of self-reference. Okay, which is, I think it's the right way to look at it. That's the right idea behind it. So last time we saw it as diagonalization. Today we'll see it as self-reference. Okay, so to see it as self-reference, let's start with a paradox, which is I think it's called Russell's paradox, or it's an illustration of Russell's paradox. Okay. So, this way of illustrating it, think of this as, there's a barber in a small village, okay, and this barber makes a statement saying, I shave every man in this village who does not shave himself. Okay? So now, given this statement, what does it say about whether the barber shaves himself? How about I shave exactly those men? I'm sorry. Yeah, that's a very good point. Yeah, so one resolution is the barber is not a man. Yeah, that's a very good. And if it was a man, then we are in trouble, right? Because if he shaves himself, then he's shaving somebody who does shave himself. And if he doesn't shave himself, he's not shaving somebody who doesn't shave himself. Okay, so he's in trouble either way. Okay, so I claim that there's a way to look at what we did, the proof that there's no program that tells us whether a given program halts on a given input. We can see that proof as an example of this. Okay? So how do we do that? So let's go back and look at the question that we are trying to solve. So what we want to know is there a program halt, which takes as input takes two inputs, such that halt on input a program and x is equal to h if p on input w halts. So if it ever halts, and L if p on w loops, or does not halt, loops forever. Right, so we are trying to design a program halt, which can decide, given an arbitrary program and an input to it, whether it'll ever halt on that input. Okay. And so then, what we said is, suppose we have such a program, then we can implement Russell's barber, who we call Turing. So Turing takes as input a program, and it says, if P halts on input P, then loop forever, else halt. Right? So exactly an analogy, right? And so then we said, again, where does the paradox lie? Well, does the barber shave himself? What does Turing do on input Turing? After all, Turing itself is a program. So what if you input Turing to Turing? So Turing on input Turing. If halt works correctly, it's going to figure out whether Turing halts on input Turing, and then it's going to do the opposite, right? So that's a contradiction. So this is a real problem, and this problem is exactly the same problem that shows up in this sentence is false, right? So the roots of it are there, and that was regarded as, that was sort of a when it was first thought of, it was just an annoying little puzzle. It was either annoying or amusing, depending upon your point of view. And then it grew and grew, and then it, sort of took over in a much larger way. So there was there's a story about, so there's an old story about a philosopher who had a chance to, who had this one opportunity to meet somebody who was known to be an incredibly wise man. It was somebody who just knew, who just had incredible wisdom about everything, and this philosopher was extremely excited, but he was only going to get a chance to ask one question. So he was thinking what to ask about. There were so many interesting questions about life, about happiness, about love, about ethics, about morality, and he couldn't decide what to ask. And then finally he had a brilliant idea. And so when he got there, he said to this man, it's such a privilege. I've been waiting for this moment for all my life, and I was thinking about what to ask you, and then finally I decided, I would ask this question. If you were in my position, what question would you ask, and how would you answer it? Was that brilliant or what? So then the wise man thought, for a couple of minutes, and then he said, I would ask exactly the question you asked, and I'd give exactly the answer I'm giving. Okay, so questions so far? Yeah.
You've shown that there's no such program that can determine if another program will halt or not.
Yeah.
But what if you just exclude the Turing program as one of the possible?
Yeah, how would you exclude that program? So, okay, well, what we can also do is we can even show that, actually maybe we'll do that. It's also hard to tell whether two programs compute the same function. So, in other words, you could exclude this program, but what about other programs that compute exactly the same thing, which have exactly the same functionality? You'd have to exclude all those as well, right? So given a program, there are infinitely many programs which do the same thing. For example, you could always add statements that do nothing, right? Or you could add a section of the code which is never executed. Right? So there are infinitely many versions of this. So you could say, well, okay, what I want to do is I want to exclude all those infinitely many programs that are equivalent to Turing. But already there's a problem, of course there's a problem, how do you exclude all those infinitely many? But even if you had the stamina to exclude all those infinitely many, you also have the problem that given two programs, it's not even computable to tell whether they are the same program, whether they have the same functionality, right? So if you had Turing and if you had this program X, which does something, you don't know what this program does, right? Now, you cannot even tell whether these are the same. And so on what basis would you exclude or not exclude X? Okay, so somehow the problem is that uncomputability is, it just goes all the way to the roots of programs. It's, all the most interesting things you'd want to do in full generality, they are uncomputable. And so you've got to scale back your sights. And, this is one of the things that there was an early lesson in computer science that you couldn't, many of the things we wanted to do, you couldn't do. Right? So let's say you want to, if you're trying to write a compiler, you would like to understand code. Well, you cannot do it in full generality, so you've got to structure it. You've got to find a small subset of it that you can understand and automatically, and then you deal with that. Yeah. Sorry. Yeah.
But for like a pure function, you just expect that the output is the same. You put input the same thing, return the same output. You can do that for a pure function, functional program, right?
Well, okay. So what would it mean to check that P is the same as X? It means checking for every input that it does the same thing. So if you want to say, are these two programs equivalent, you want to say not only are they equivalent on a particular input, but are they equivalent on all inputs? And that's very hard, right? But then, even if you're checking on one particular input, are they the same? Well, what if X on that input just takes a very long time? How long do you wait for it to output what it does? So maybe on a particular input, P and X are the same. Right? They output the same thing, except X takes an incredibly long amount of time. Now, how patient should you be before you decide, right? How do you distinguish that case from one where X actually loops forever? So in the one case, X halts, but after a very long time, and then it outputs the same thing as P. In the second case, X just loops forever. Right? How do you tell which case it is? Well, in order to solve that, you need to solve the halting problem. That's uncomputable, undecidable. Yeah. Could you exclude self-referential programs? There was... so people tried to do this. People tried to do this not in the case of programs, but in the case of mathematics. They were trying to do logic, and they tried to come up with exclude all the self-referential statements. And Russell and Whitehead tried very hard to do this. They spent years doing this, and about the time that they were done, they discovered that there was another paradox that you could introduce. So it's just very hard to do, or it's impossible to do. Yeah? Yes.
I'm wondering, we're assuming that these programs are all deterministic, correct?
They are all deterministic. Yes.
So could you keep track of the state of the program?
Yeah.
And then, if you wind up back at the exact same state that you were, if you wind up at the exact same state that you were at previous time, then obviously you're going to.
That's a very good point. So the question was, well, can't you keep track of the state of the program as you go along? And if it ever repeats a state, then you know it's in a loop. And then it's going to loop forever, right? If it ever repeats the same state twice, if a program ever repeats the same state twice, then you know it's stuck in a loop and it's going to keep looping forever. And that's true. That's one kind of loop, right? But another way it could loop forever is it just keeps going, but it never repeats the same state. So, for example, if it keeps adding 1 to a counter, well, it'll never, so maybe not, maybe with a finite amount of memory, but if we idealize it, okay, so we know with any with any particular program on an idealized machine, if it was just counting, if it just added 1 to a count at every step, it would just keep going forever. But it never repeats a state, right? And so there are types of programs which can keep going forever, but they never repeat a state, and then you would never catch them. Yeah? Okay. Okay, so there were these questions. Well, could we use it's so we know that Turing on input, Turing is, that's a hard thing to catch, but how often do we want to run a program on its own on the same input? What about if all you care about is, does P halt on input, say 0? Right? Surely that's easy to do. Okay? I mean, surely that's not a hard thing to do. Okay? And, well, the answer is, it's, in fact, even this is hard to do. Even deciding whether P halts on input 0, there's no program that can tell you whether P halts on input 0. And the way you prove this is by showing that if you could solve this problem, then you can solve this halting problem. Okay? So what we'll do is we'll say, if there's a program let's call it E-halt for easy halt of P that solves this problem. Then there's a program halt Px, okay, which tells whether P halts on input X. Okay, so once we show this, then we know that there's no such program as well, because we know this doesn't exist, therefore this can't exist. Right? Okay, so this is called a reduction. Now it's saying, well, okay, so the way it works is we are going to take this problem. So the way we'll show this is we start with the question, does P halt on X? And now we convert this into a new question. Does P prime halt on 0? Okay? And we'll do this in such a way that the answer here is yes, if and only if the answer is yes here, meaning it's no here, if and only if it's no there. Okay? So we can answer this question if we can answer that one. But we know that we can't answer this. Therefore, we know that we couldn't possibly answer that one. Okay? So the way we say this is we are reducing this thing, which is the halting problem, to this one, which is easy halting. Okay, is it clear? Okay, so how do we do this? How could it possibly be that we want to know, does P halt on input X? And now, how could we figure out the answer to this by asking whether some program P prime halts on input 0? What happened to X? Yeah?
Do we only use the fact that the arrow can go from right to left?
I'm sorry?
So the yes
This one? Do we need both sides of the arrow?
Yeah, we only need the arrow going to the left, right? Then if you could solve the P prime problem, then you could solve the P problem.
Yes.
That's the only arrow we need.
Yeah, and that's why the arrow we have here is only in this direction. Right? We start with this problem. Does P halt on X? This is the one we really want to solve because we know that that's hard to do. Right? So we start with the fact this problem is hard. Now, we want to show this one is hard. Right? So we say, look, I bet you can't solve this problem because if you could, then you can solve this impossible problem. And so the way I'll show that you can solve this impossible problem is I start with this problem. Okay, ask me anything. Okay, does P halt on X? And now I'll take it and I'll massage it into another problem. Does P prime halt on 0? So I massage it into an instance of this other kind of problem. And now if you can solve this easy problem for me, then because of this two-way correspondence, yes, no, I know that whatever you answered me here is the same answer that I had on this side. And so I've actually answered this question, which I wanted to. But this was the impossible one to answer. And so the only way this could happen is if this is also impossible. Okay? So now, how do we create this arrow? Right? This is the main thing we want to create. How do we take P and X and map it to P prime and 0? Okay, so how do we do that? This may be confusing only because it's so simple. Right? I claim that the only thing that's hard about this is that it's so simple you won't even think of it. So how would you do this? If I give you a program and an input, how would you write a new program that halts if and only if this one does? Yeah. Yeah, you just define P prime as returning P of X. So you build X into P prime. Right? You build X as a constant in P prime. Right? So P prime is just the program on input anything. Return P of X. Right? So you just build in P and build in X into the program P prime, and that's all you do. So basically the way we want to think about this is we have a subroutine. We have this subroutine for easy halt. That takes as input P prime, and it tells us, does P prime halt on? Okay. And you're given such a subroutine, and what you want to do is design a program that solves the halting problem. So you build around this subroutine, you build a larger program that takes as input P and X, and it should tell us, does P halt on X? And what you do in the process of calling the subroutine is you massage P and X, and you create P prime, you input it. Okay, once. You could also input it many times if you wanted, whatever it takes to solve this problem. You solve it using the help of this one, right? But at the end of the day, if using this subroutine you can solve this problem, and if this problem was impossible to solve, then you know that this subroutine does not exist. Right? Okay. Okay, questions? How are you doing on stamina? Take a minute break. Hi, yeah. I'm sorry, yeah.
So, like, as humans, we can somehow figure out that some programs halt or not. Like,
I'm sorry, yeah.
Like the counter thing
Sure.
you're talking about, we can figure out if, like, the counter is on forever
Yeah.
just by looking at the code.
Sure.
And so, can't we somehow employ, like, those heuristic, like, skills that humans have?
You could, and you can figure out some programs whether they halt or not, but not all.
Right. Okay. So it's not just, like...
Okay. Okay, so there were two questions that were very central in logic about a century ago, about the beginning of the 20th century. So these are the two questions that were essentially posed by Hilbert about the year 1900. So what do these two questions say? Is arithmetic consistent? So if you look at the natural numbers, right, together with the axioms that we talked about, the axioms for natural numbers, the induction axiom, and the axioms about addition and so on. Okay, so Peano's axioms for the natural numbers, and you ask, is it possible that using these axioms and our rules of inference, is it possible that you can ever get a contradiction? Is it possible that we'll derive some statement, that using these axioms and the rules of inference, we'll be able to derive some proposition P, and then we'll also derive the proposition not P. Okay? If we ever do that, then that's a complete disaster. That would mean that arithmetic is worth nothing, right? There's no point studying it. Is it clear why it would be a complete disaster? Right? As soon as you have a contradiction like this, as soon as you derive P and not P, from this you can derive anything you want, right? Because this implies false, and false implies anything, right? So you remember this Okay, let me try again. Remember I told you the story about Bertrand Russell? About how he finished his tome about arithmetic and, trying to axiomatize it in this way. And he was trying to explain how if you ever had a contradiction in mathematics, that would be a disaster, because from a contradiction you could derive anything you wanted. For example, and then he said, for example, if 1 equal to 2, then I can prove that I'm the Pope. And, okay, again, so one of the reporters asked, well, how would you do it? And now, okay, so so as soon as you get a contradiction, you can derive anything because false implies anything. That's the truth table, right? False implies anything. But how do you explain that to a reporter? Okay, so without missing a beat, what he did was he said, consider a set of with two elements, me and the Pope. So if 1 equal to 2, okay, it's a set of 2 elements. No? No? Okay, so maybe I have to say it the way he said it to the reporters. Okay, so he actually said it a little more gently. He said, consider a set with 2 elements, me and the Pope. The Pope and I are 2, but we are 1. So that's consistency. Now there's another property that you would want arithmetic to have. Yeah, sorry, go ahead. No, it's just you don't want a contradiction. You want to be able to prove, so if everything is true, then if everything is true in arithmetic, then what's the point studying the theory, right? What you want is for it to be meaningful, and only you want only true things to be true in the theory, right? Things that actually hold for these numbers. Now, the other thing the other property that you want is completeness. So there's those, so you can make a statement. For example, Fermat's last theorem, right? There do not exist x, y, z such that x to the n plus y to the n equal to z to the n for all n greater than or equal to 3. Okay, so this is a statement which is either true or false. It either holds for all numbers or it doesn't, right? But then, is there proof for it? So for the longest time, there was no proof for it. We didn't know whether it was true or false. We didn't have a proof, right? And then after a very long time, after a couple of 100 years, there was finally a resolution a few decades ago when this was actually proved. Now you'd like to know, is it the case that every true statement can be proved? Right? Can we prove every true statement, or could it be that there are some true statements which cannot be proved in the theory? Okay, so we'd like to show that the arithmetic is both consistent and complete. Now what happened in 1930? I think it was, this problem was posed, this question was posed by Hilbert about 1900, and then in about 1928, he finally sat down and precisely posed it in these terms. He said, is it really consistent? Is it complete? He sort of posed it in full detail. And then a couple of years later, Gödel came around, and he showed. So everybody believed that the answer was yes, and the only question was, how do you prove it? So in fact, Hilbert didn't ask the question, is it consistent, is it complete? He asked, can you prove that it's consistent, and can you prove that it's complete? Because nobody believed that the answer could possibly be no. And then a couple of years later, Gödel showed up, and he proved that in fact the answer is no. And the way he proved it was through this connection between proofs and computation. Right? Of course, at that time, there were no computers, and nobody knew what computation was. And so he actually had to invent it. But when people invent something, often they don't know what they've done. And so Gödel did not know that he had invented computation. It was sort of buried deep inside his proof. Okay? And it was a few years later, I think it was in 1936, that Turing actually sort of put his fingers on this notion of computation, and he actually defined what a computer is in the form of a Turing machine. Okay, so somehow computation was inherent in here, and then it got excavated, and Turing actually defined it. And then he defined not only this model of computation, Turing machines, he also defined the whole notion of a program. How do you program a Turing machine? And then he proved that the halting problem is uncomputable, that there are all these problems that you really cannot solve on a computer. You can't solve arbitrary problems on the computer. And in fact, this proof of Gödel's was a very complicated proof. It was a very hard proof to understand. At that time, it was considered, that very few people, a handful of people, really understood that proof. Today, what we can do is, I can tell you the essence of the proof in the remaining however much time we have in this lecture. And the way we'll do that, again, is because we understand computation today, right? People didn't at that time. And so what we'll do is we'll sort of understand this problem, and then we'll use the fact that the halting problem is uncomputable. It's undecidable, right? So, and we'll use that fact to show that, in fact, there's no, arithmetic is either inconsistent or incomplete. Right? So this was called Gödel's incompleteness theorem. Okay, so how does this work? Well, imagine that you have a formal system, F. This represents arithmetic. Okay. By F, I mean these are the axioms of arithmetic, right? Peano's axioms and any other axioms you have to throw in to make the theory complete. Okay, so you have your theory. It consists of the axioms and the rules of inference, and that's your theory you're working with. And now, once you get to arithmetic, the reason arithmetic is because arithmetic is powerful enough that you can use it to express computation. Okay, you can express the fact that you have a Turing machine or some model of computation, and it's computing something. Okay, so in this theory, it's powerful enough that you can write a sentence. So we'll write a sentence S of F. And S of F is going to be the sentence. So this is going to be the sentence which says, this sentence is not provable in F. Okay? So it's a sentence which says, if F is arithmetic, that says, this sentence is not provable in arithmetic. And so this is what Gödel did. He created this kind of a self-referential statement. Now, once you manage to do this, it's easy, right? Because there are two possibilities. Either it's provable or it's not. So case one, it is provable. Okay, what's wrong with that? What's wrong if this sentence is provable in F? Well, then you prove it, and then it's true. Okay? If it's true, then it says it's not provable. So you got a P and not P. You prove P and not P. You got inconsistency. Right? Case 2. Not provable. Okay, what happens? What goes wrong if it's not provable? It's not provable. So what's wrong with that? Well, it's not provable, so, and this sentence is saying it is not provable, so now what can you say about this sentence? Is it false or true? It's true. Okay, so it's not provable, implies it's true. So now, why is that a problem? Well, here's a true statement which is not provable. Okay, so it says that arithmetic is incomplete. There are true statements which you can't prove. Right? So Gödel was telling us arithmetic is incomplete. It's either incomplete or it's inconsistent. Right? Inconsistent is really bad. Right? Incomplete, well, it's bad, but we can live with it. Okay, so now, how do you actually write such a sentence? Okay, so to write such a sentence, you have to work really hard. Okay, and this is what Gödel did. Okay. At Gödel's time, you had to work extremely hard because he was he was constructing a programming language from scratch, just with bare hands, right, using arithmetic. Today, you could do it a lot. It's a lot simpler to do because we understand what programming means and how to construct such a language. So it would be easier, but still, it would be quite hard to do. There's a much easier way to do this, to prove his theorem, and that's to use the halting problem. Okay? Okay, so what do we do? Well, we want to understand, does P halt on 0? Right? We showed that this is not something we can ever compute. We can't ever hope to compute this for general P. By the way, sorry, let me clarify one thing, just going back to this. When I said the halting problem is uncomputable, it doesn't mean that for particular programs you cannot tell whether they halt or not. Right? I can give you a simple program and you'll be able to tell, does it halt on this input or not? In fact, when you go on to CS 170, I hope you'll be able to prove that all the programs that you write do halt. Right? Because you're supposed to be able to analyze them and say, okay, this program not only halts, but it halts quickly in this much time on this input. Okay, so halting is easy for some programs, and that's the reason why you can write compilers. Right? When you write a compiler, you're saying, if the program is written in this format, then I can analyze it, or I can analyze certain fragments of it, and that's a good thing. But what this is saying is, in full generality, you just cannot. You can't analyze a program. Right? You cannot ever tell whether it halts or not. Okay. So now this is a general program. I want to know, does it halt on input 0? Okay. So I claim that this is something, this statement, does P halt on input 0? This is a statement in arithmetic. It's either true or false, right? Okay. And if arithmetic was consistent and complete, then there'd be a proof either way. There'd be a proof either that it halts or it doesn't halt, right? So if arithmetic is consistent, complete, then there's a proof either way. Okay, now what's a proof? Well, a proof is just a string, right? You can just write it out in some language, in binary, let's say, or in a tertiary alphabet. So a proof is a certain string, right? It's just a string. If you could write it out in ASCII, and now you'd have 0, 1, 0, 0, etc. You could write it out in as some binary string, and it's going to be a finite binary string. Now, how many proofs are there? What's the total number of proofs there could be? Could it be uncountable? How many finite binary strings are there? It's countable. Okay, so it's countable. Let's just go ahead and write out all of them one after the other. Let's just go through them one after the other, all possible proofs. Okay, so we could just take a machine M, which does this. It just goes through every possible proof. And halts if it finds a proof that P halts on input 0. Okay, M is such a machine, and then you can also make up M prime, which is a similar machine which halts if it finds a proof that P does not halt. Okay? And now if you can solve the halting problem, you can decide which of these machine halts. And whichever machine halts, it'll tell you whether P halts on 0 or if it does not halt on 0. So if you could solve the halting problem, I'm sorry. So it's the other way around. We start with the halting problem. We start with the question: does P halt on 0? Right? And now, sorry. Let me say this again. It's a little bit subtle. So let me say this again. Okay? So. Let me write this out a little more clearly. Okay, so we are trying to decide, does P halt on 0? Okay, we are assuming that arithmetic is consistent and complete, meaning that anything that's true, there's a proof of. Okay, so now whether P halts on input 0 or it does not halt on 0, there's a proof that, in either case, there's going to be a proof that it halts or does not halt on 0. Okay, so now what do? Well, we write a program M which does this. Okay, it goes through every possible proof X. Okay, and then it checks. And then it checks if X is a proof that P halts on 0. Okay, so then it says yes. Then it outputs yes. It also checks if X is a proof that P does not halt on 0. And if so, then it outputs no. Okay? But now, regardless of whether P halts or not, there's some proof that in either case there's a proof that it either halts or does not halt. So at some finite point, M has got to stop because it'll come across a proof either that it halts or that it does not halt. So it'll always halt and either output yes or no. Right? Okay, so now M is our machine halt, which tells us whether P halts on input 0. But that's impossible, therefore M does not exist, and therefore our assumption here was incorrect, and therefore arithmetic couldn't possibly be consistent and complete. Okay, so what we've shown is that somehow, the uncomputability of the halting problem implies that one of two things must happen. Either arithmetic is inconsistent, meaning that it's a complete disaster, right? Or it's incomplete, meaning you can't possibly prove every true statement about numbers, right? There are statements about numbers which are true, but you can't ever possibly prove them. Okay? And the reason you can do that, again, what does this rely on? What it relies on is the fact that if you're given a proof, right, not the kind of proofs that we've been writing. We've been writing proofs where we skip steps. We make them so that they are easy to read humanly. But if you write out a proof in full generality, like we did, for a little while in the first, right in the beginning of class, beginning of the semester, we were writing out proofs where we'd say, okay, so for every step there's a justification, and it was all very, very detailed. And now you could actually imagine writing a program that checks through the proof, and it checks, is this a correct proof? And then if it's a correct proof, did it actually, then it actually proved what it set out to. So imagine that these proofs X are written in that level of detail, right? So that you can actually have a program that goes through and automatically checks, is this proof correct? And is it really proving that P halts on input 0? Right? If you have such a proof, you can actually check it, and you can write a program that checks it. And similarly, if you have a proof which shows that P does not halt on 0, well, okay, so it's a step-by-step thing where each step follows from the previous one by just a simple rule. And that's something that a program can check, right? You can write a program to do that. And that's your program M. It just checks the proofs, right? And now what else is it doing? It's taking every possible binary string one by one. It's enumerating all possible binary strings and laboriously going through one after the other, checking, is this a proof or not? Now, how do we know it won't run forever? Well, the reason we know is because there's only one of two possibilities. Either P halts on input 0 or it does not. Okay? In either case, we know, because arithmetic is consistent and complete, that's what we assumed. We know if it's complete, we know that whatever the truth is, there's a proof of it. Right? So either there's a proof of this on this side or there's a proof on this side. Meaning we can't keep going forever because whatever the proof is, you'll be enumerating every possible number. So we'll eventually get to this one. And we'll stop because it's either a proof for this one or that one. So we can't possibly loop forever here. This program is guaranteed to halt and either answer yes or no. And it's guaranteed to be the correct answer because of this, because consistency and completeness. Right? Okay, so that's where this tie-in comes in between computation and proofs. Right? At a very deep level, right? The connection is extremely deep, and it's also a historical connection because this is how computation was discovered in the first place. Okay, so sorry, that's yeah. then we would actually be able to decide whether P halts on input 0. Oh, because because within arithmetic is sufficiently okay. So what I'm doing is I'm suppressing one detail, which is that arithmetic is sufficiently it's a sufficiently rich theory that within arithmetic you can actually formalize the notion of a computation or a computer. You can actually say, you can actually formalize. So you can write a proof that P halts on input 0, right? Okay, so in other words, whether P halts on input 0, well, what that means is, well, you have various steps in the computation where you add 1 to x or multiply by 2 or check whether the answer is positive or negative and so on, and you keep doing these steps, and that's what your program looks like, and you can express all that in arithmetic, right? So this statement, does P halt on input 0, is something that is a statement about numbers eventually. Okay, and then because it's a statement about numbers, you can actually, it's either true or false. Then, oops. So then there's a proof of it, right? And so and because there's a proof either way, then okay. So this is how the connection comes up. Okay. Yeah. Yeah. Well, Gödel's statement is more complex, right? If you really want to work through all of it, it takes a lot of doing, but this proves a very big chunk of it, right? So from our point of view, it proves enough of it that the connection's established. Now, in actual fact, yeah, there are many bells and whistles in Gödel's statement, and actually pinning those down takes a lot of work. Okay. Any other questions? Yeah.
Is this theorem sadden you or make you happy?
Yeah, that's a good question. Once upon a time, when I first came across it, it was I thought this was an extremely sad statement. My perspective on it has changed greatly over the years. Now I don't think it's I think it's that's reality. That's how things are. It's actually not a bad thing. What do you think?
It's interesting.
It's interesting. Yeah, it makes life more interesting, doesn't it? Okay, thank you.